Okay, in this video, I'm going to go through the Cambridge International A-Level chemistry. And this is paper 2. This is the one that covers the AS content. And this is the 2019 paper. Okay, so the first question is about group 2 elements. Okay, it says calcium reacts more quickly than magnesium in cold water because more energy is required to remove the outer electrons in magnesium. Okay, this occurs even though calcium's got a greater nuclear charge. Explain why more energy is needed for magnesium than for calcium. Okay, I would state here that the electrons in magnesium are being removed from the 3s orbital, whereas in calcium they're being removed from the 4s orbital. All right, now it requires less energy to remove it from calcium because these electrons, they are further from the attractive force of the nucleus. And also because you've got more intermediate shells, you've got greater shielding. They are the two marking points there, the distance and the shielding. Okay, now we have got strontium reacts with an excess of cold water. When the reaction is complete, a colorless solution is seen. Construct an equation. Okay, so we've got strontium solid metal. Now when that reacts with water, you get a solution of strontium hydroxide, which is that. It's got a formula for strontium forms a 2+ ion, and you get hydrogen gas formed. That's an aqueous solution. To balance out, we're going to need 2 waters. Okay. Right, now you put the same 0.05 mole of calcium and the same number of moles of strontium into 2 beakers, and each beaker contains the same amount of cold water. At the end of the reaction, a white solid and a colorless solution seen in both beakers. Now, you may think, well, where's the white solid coming from? This is because in this equation here, strontium hydroxide is soluble, but when you've got too much of it, of course, you will get a white precipitate of strontium hydroxide. And you've obviously got too much here. Predict which element, calcium or strontium, produces the more alkaline solution. Explain your answer. Right. You're going to get a more alkaline solution with strontium because the reason for that is strontium hydroxide is more soluble than calcium hydroxide. Okay, so you've got a greater concentration of OH- ions with the strontium, and that means you're going to have a higher pH. Okay, so it's due to the solubilities of the hydroxides. Describe one observation when magnesium carbonate is added to dilute sulfuric acid. Right, if you added any carbonate to an acid, you are going to get CO2 release, so you're going to see effervescence or fizzing, and that is that's the observation you're going to get. Also, you're going to form magnesium sulfate, which is soluble. So another thing you could say is the solid dissolves. Okay. B. Element X is a metal. X reacts with oxygen to form a black solid oxide. Okay. The oxidation state of X of the metal is +2. Okay. From the information given, state 2 similarities and 1 difference that the metal X and its compounds have with group 2 metals. Okay, from the information given. Right, similarity is that they both X and the group 2 metal will have an oxidation state of +2. Okay. Another similarity is that group 2 carbonates will also decompose they will also decompose to give, for example, you get the formula M CO3, where M is the metal, that's the carbonate, is going to give you the metal oxide and CO2, so they'll both decompose in the same way. A difference, I would say, is that group 2 compounds are always white, whereas this is this one is a green solid. It's probably copper carbonate. Okay, colored compounds for X. X is a transition metal. As I say, it is copper probably. The transition metal compounds usually colored, whereas group 2 compounds are colorless, white. Okay, right, the formula of the oxide of X, well, it's got to be XO. And the reason for that is because we know that's got a +2 oxidation state, so it must be existing as a 2+ ion. And the formula of the oxide ion is 2-, so that's how we know that. Okay, an equation for the reaction of X when it's heated, right, it's going to undergo thermal decomposition. So you're going to get X CO2, CO3, sorry, goes to the oxide and carbon dioxide. I haven't bothered putting the state symbols in there. Okay, magnesium silicide, Mg2Si, is a compound made by heating magnesium with sand. Okay, draw a dot cross diagram to show the arrangement of the electrons and assume magnesium silicide is an ionic compound. So we've got magnesium, which is 282, and we've got silicon, which is 284. So presumably we're going to form an Mg2+ ion. And silicon is going to gain 4 electrons to form an Si4- ion. So we'll just show the outer electrons. So the outer electrons in magnesium, well, you're going to have 8 in that outer shell, aren't you? So I'll put a 2+ there. And we're going to need 2 of those, so times 2. And the silicon, well, that's going to look like the outer shell. So silicon is going to have 4 of its own electrons, which just draws the dots, and then it's got these 4 crosses, which it has gained from the magnesiums. So that is going to be 4-. Okay. When solid magnesium silicide is added to water, silane gas, SiH4, and a solution of magnesium hydroxide are produced. Construct an equation for this. Okay, so you know, don't need to know this, but they've given you most of the information. Okay, so it's not so you need to know. So magnesium Si, that's going to react with water. Okay, it's going to give us magnesium hydroxide, which has got that formula. And it's going to give us silane, which is that. Now we need to balance that. We are going to need 2. Let's think. We need to have 2 of those, don't we? So that means we need 4 oxygens. So we need 4 waters. And that will give us the right number of hydrogens on both sides of the equation. Okay. And we need state symbols where it says this is a solid, water is a liquid. Magnesium hydroxide is very insoluble, so that's going to be a solid. And silane, they tell us, is a gas. Suggest with reference to structure and bonding why SiH4 is a gas at room temperature. Okay, so it is a simple covalent molecule. And it won't have a permanent dipole because it's symmetrical. So you only get weak van der Waals forces between molecules. So, and they don't require much energy. Always worth putting that in. Not much energy needed to break them. To break the van der Waals forces or the London forces. Okay, right. The table shows the electronegativity values of carbon, hydrogen, and silicon. Okay, the carbon, hydrogen, and silicon hydrogen bonds, you don't have complete even sharing of electrons in them because the electronegativities are not exactly the same. So we've got to show the polarity there. So if you look at the carbon, it's slightly more electronegative than hydrogen. That's going to have a small negative charge, delta negative. That's going to be delta positive. It's going to be the other way around in the silicon hydrogen because silicon is less electronegative than hydrogen. So that is going to have a small positive charge, and that's going to have a small partial negative charge. Okay, explain why methane has no overall dipole moment. Right, now as we see in there, here, the bond is ever so slightly polar, but there's no overall dipole because it is, methane is a tetrahedral molecule. So I'd write that down. It's tetrahedral. Therefore, it's symmetrical. It's got symmetry. So the partial positive charge is on the hydrogens all cancel each other out. They're all kind of pulling against each other. Okay. Xylene reacts in air without heating, but CH4 must be ignited before the combustion occurs. Suggest with reference to this, exactly the same equation really, as you can see there. Suggest with reference to bond energies from the data booklet why SiH4 reacts without heating, but CH4 must be ignited. Well, if you look from the data book, if you look at the bond enthalpy values, the carbon-hydrogen bond is stronger, okay? And so the activation energy for the reaction is going to be greater there than it is for the greater activation energy required to break the the carbon hydrogen bond, and so that's why it is it's the silane is more reactive. Okay, silicon dioxide reacts with hot concentrated sodium hydroxide. So this is something you just need to know. You need to know how the acid base behavior of your group period 3 oxides, and it's actually an acid base reaction, which is actually that in question 2. But here we get SiO2 reacting with NaOH, and it forms sodium silicate, which has the formula Na2SiO3. So that's sodium silicate, and you also get water. So they're the two products. It doesn't ask you for the equation, actually, does it? It asks you, let's balance it anyway. It asks you for the two products, which are sodium silicate and water. And if you think that's may seem quite unfamiliar, but silicon is in group 4 of the periodic table, as is carbon, and sodium carbonate, that's quite a familiar chemical to us. And the sodium silicate is kind of analogous to that. The behavior of the silicon dioxide during this reaction, it's acting as an acid. Silicon dioxide is an acidic oxide. Right, construct an equation for the second ionization energy of argon. Okay, so second ionization energy is removing the second electron, so one electron's already gone. So we're going to have AR, the gaseous state, and it's going to be a positive ion. And it's going to lose another electron to form Ar2+, which is a gas, and another electron. Okay. The graph shows successive ionization energies for the element argon. Complete the graph with predictions for the 8th and 9th. Okay, so we've got the first set up to the 7th there. Now, if you look, this is the electronic structure of argon here on the right. And so we have got 8 electrons in the third quantum shell. Okay, now for this part here, you're just getting a slow increase. Okay, and that would continue to remove the eighth electron. So the 8th I'd put about there to continue that trend. But when you come to remove the 9th electron is not coming from the third quantum shell, it's coming from the second, it's coming from 2p. So that's going to be much higher. So I'd put the 9th, it's not going to be as high as that one up there, but it'd be something like that. Okay. So they are the 2 crosses you've got to draw. You're getting that jump as you're going from the third quantum shell to the second quantum shell. Okay. The energy value required to remove the first electron from an argon is circled on the graph. This gets the shape of the orbital that contains this electron. Well, it's that first electron, that's drawn the electronic structure, it's coming from 3p, isn't it? So what shape does the p orbital have? It is like that. Okay. Right, now we have got an ideal gas calculation. Right, chlorine exists as diatomic gas, Cl2. Sample of Cl2 was measured in a chemical reaction. It was measured at, gives you the pressure, it gives you the temperature, 25 degrees C, of course that's 298 Kelvin. We need to use Kelvins in the ideal gas. Yeah. And the sample occupied 20 centimeters cubed. Calculate the mass in grams of the chlorine formed. Now, first of all, what we've got to do is we've got to find out the number of moles of chlorine. Once we've got the number of moles, then we can do the mass of chlorine is going to be equal to the moles multiplied by the MR of Cl2. So let's first of all, we have PV is equal to nRT. We'll rearrange that to get N. So we've got N is equal to PV over RT. Let's put the numbers in. Okay, now we have to be careful because pressure is not, in the ideal gas equation, you've got to put it in pascals, not kilopascals. So that's times that by 1,000, so 404,000 multiplied by, I've got to be really careful with the volume. Volume is 20 centimeters cubed, but that's got to be converted into meters cubed. There are 1,000,000 centimeters cubed in 1 meter cubed. So that 20 is going to be divided by 1,000,000. 20 divided by 10 to the 6. That's the volume in meters cubed. And then we want the ideal gas constant, which is 8.31. And the temperature in kelvins, which is 298. Put that into a calculator and you get 3.26 times 10 to the minus 3 moles of chlorine. Now we need to work out the mass of chlorine. So mass, as we said, is equal to moles times by the MR. Okay, so the moles is 3.26 times 10 to the minus 3. And the MR of chlorine, well, that's 2 times 35.5 because it's CO2, which is equal to 71. And that gives us 0.232 grams. I'm going to give it to 2 significant figures because that's the least accurate bit of data there. That's only given to 2 figures, so let's put 0.23 grams. Okay, that is our answer there. Now, question 2, I think it asks you to work out, I haven't put it there. Question 2 asks you to work out the number of atoms in the sample. Not of molecules, number of chlorine atoms in the sample. Well, we need to work that. We know the number of moles of Cl2 we worked out earlier is that. So the moles of chlorine atoms is going to be double that. Each molecule contains 2 chlorine atoms. Is equal to 2 times 3.26 times 10 to the minus 3, which is equal to 6.52 times 10 to the minus 3. Now we need to work out the number of atoms using the Avogadro constant. So let's do that. Number of atoms. That's going to be equal to the number of moles multiplied by the Avogadro constant. So that's 6.52 times 10 to the minus 3 multiplied by 6.02 times 10 to the 23. That's the Avogadro constant. And that gives us 3.93 times 10 to the 21 atoms. Okay, so that is using the Avogadro constant, and you've got to be careful with that one because we know we're talking about moles of diatomic chlorine, and then we're talking about moles of chlorine atoms. So that's why you've got to be careful really with that. Okay, chlorine does not behave, part 3, chlorine does not behave as an ideal gas under these conditions. Explain why chlorine behaves even less ideally at very high pressures. Well, at very high pressures, the molecules become close to each other. And so there are intermolecular forces of attraction, obviously, between the Cl2 molecules. And the ideal gas assumes there's no attraction between them. So I would say that for very high pressure. You could also say at very high pressure. Another acceptable answer is to say that we assume that the volume of the gas molecules themselves is negligible. When they're very close together, that ceases to become true. The volume of the gas is actually comparable to this volume of the container. So that's another reason. At very low temperatures, why does it behave less ideally at low temperatures? Is because the molecules have got less kinetic energy, and so they are attracted to each other. The intermolecular forces between the molecules are significant. Okay, well, again, the ideal gas law states the volume of the gas molecules is 0 and there are no attraction between the molecules, which is not true of those two things. Okay, onto organic chemistry. Right, we've got Y. Give us a systematic name for Y. Well, we have got 3 carbons, 1, 2, 3. So we would call that, it's propene, isn't it? But we would call it 3-chloro-prop-1-ene. Okay. Predict the values for the bond angles A and B shown in the diagram. All right. Now A, that carbon is tetrahedral. It's got 4 bonding pairs, yeah, and no lone pairs. So it is tetrahedral. So that's going to be the tetrahedral bond angle, which is 109.5. If you look at the carbon atoms in the double bond here, B, they've only got 3 bonding pairs. Okay, remember when we're looking at shapes of molecule, we just assume we pretend a double bond is like a single bond. So we've got 3 bonding pairs, no lone pairs. So that's going to be trigonal planar shape around that carbon atom. And so the bond angle there is going to be 120 degrees. Okay, when Y reacts with cold, dilute acidified manganate, a compound Z, so you get the diol, the double bond breaks, and and you break the bond there. State the molecular formula of Z. Well, we have got 1, 2, 3 carbons, so that's C3. Hydrogens, we've got 2 there. We've got 2 there. We've got 1 there, 1 there, 2 there, and 1 there. So that is 7 hydrogens altogether. And of course, we've got 2 oxygens, O2, and 1 chlorine. So that is the molecular formula of Z, and you've got to be careful with your numbers of hydrogens there. Maybe safer to draw that, skeletal formula into a fully displayed formula to be on the safe side. Right. And name the type of reaction when Y is converted to Z. So just to remind you there, Y is converted to Z here. Okay, sorry. And of course, it is an oxidation reaction. Potassium manganate is an oxidizing agent. Okay, alcohols can be classed as primary, secondary, or tertiary. Identify with the tick the alcohol groups present in Z. Okay, so let's have a look at Z. Right, this alcohol here is attached to this carbon, the red one, which is attached to one other carbon. So that is a primary. And then let's have a look at this alcohol, the green one here. Right, that is attached to that carbon, and that green carbon you can see is attached to 2 other carbon atoms. It's attached to the yellow one. Sorry, the yellow one and the red one. So that is a secondary alcohol. And there are no tertiary alcohols there present in Z. Okay, samples of organic compounds A, B, C are placed in unlabeled bottles. Identify all the compounds that contain a carbonyl group. So I've drawn them out rather than these. When they draw a formula on a line like that, it is quite confusing sometimes, and sometimes maybe worth actually drawing it, taking the time to draw it out. So which ones contain a carbonyl group? Well, you can see we've got a carbonyl group there. So A's got one, B has got one, C has an ethanol, and D has got one. So it's A, B, and D. Okay. Right, A to D are reacted with the reagents given in the table below. Okay. Complete the table. Identify which of the compounds react with the reagents and give the observations. Okay. So let's think about the first one, Tollen's reagent. That will identify aldehyde groups. And the only one of those that's got an aldehyde group is B. There's the aldehyde functional group. So it will identify B. What will happen? Positive test with Tollen's reagent, you get a silver mirror forming. Right, an alkaline solution of iodine, right? This is the iodoform test, okay? And the iodoform test will recognize it. Well, you get a yellow precipitate if you have a methyl group next to a carbonyl or a methyl group next to an alcohol. So we're looking for either of those two things. As you can see, A does have a methyl group next to a carbonyl, so A is going to be identified. B won't. C will, because it's got this as ethanol. It's got a CH3, which is next. It's got next to an alcohol, so that will also react with it. And carboxylic acids, it will not give a positive iodoform test, even though you've got that methyl next to a carbonyl. That doesn't give a positive test with the iodoform. Right, iodoform is a yellow precipitate. Will form. Okay, the last one, sodium metal. Well, sodium metal will react with alcohols or carboxylic acids. So we can see sodium metal, it will react with ethanol because you've got an OH there, and it will also react with the with D, C and D, but no reaction with A and B. C and D, what happens? You get effervescence, you get hydrogen effervescence, and the metal will dissolve. It's an observation it wants, so you shouldn't really say produces hydrogen because you can't tell it's hydrogen by looking at it. You should say effervescence, but it is hydrogen gas there. Okay. Right. We've got a reaction nucleophilic addition. Okay. Ethanol reacts with a mixture of HCN and sodium cyanide to make 2-hydroxypropane nitrile. Explain the meaning of the term nucleophile. Okay. Right. So a nucleophile is defined as a lone pair donator. Okay, and the species acting as a nucleophile, well, it's the cyanide ion, and it's the lone pair on the carbon is donated, and that, of course, is donated to the and that mechanism. The cyanide doesn't ask you this, but just that if you've got a partial positive charge on the carbonyl carbon, that's what happens there. So it's a lone pair donator, and the cyanide ion is the nucleophile. Right. So the product 2-hydroxypropane nitrile exists as a pair of stereoisomers. Okay, what kind of stereoisomerism? Well, you can see that this carbon here, I'll draw it out. This carbon here has got 4 different groups attached to it. If I just draw that out, so semi-displayed. You have got this carbon here has got is asymmetric. Draw 3-dimensional diagrams of this pair of stereoisomers. Okay. Right, so they are non-superimposable mirror images of each other. So I'm going to draw one first. So here we've got the carbon, and we'll have that OH coming out of the page towards you. We'll have the methyl going back into the plane of the paper, the hydrogen in the plane of the paper. And the cyanide in the plane of the paper also. And let's draw an imaginary mirror there. Okay, and the mirror image of that one is going to be like that. I just pretend it's reflected there. Draw it. So there you have, it should be dotted, sorry. Okay, you've got, they and indicate the chiral carbon. There's that one. There it is on that one. Okay, there are the 2 stereoisomers. Okay, give the structure of the organic product of the reaction of the propane nitrile with dilute sulfuric acid. Well, it's the cyanide group becomes hydrolyzed to form the carboxylic acid. So I will just draw. That's what we've got to start off with. When we reacted it with the with the acid, what's going to happen? You get that gets turned into a carboxylic acid. So you'll get that, which is actually lactic acid, I think. Yeah. 2-hydroxypropane dioic acid. That is the end of the paper.